Hello students, welcome back to another great section of this class. So you know what, the best thing you can do now is to ensure you have subscribed to this channel, and please don't skip any part of this video. It's very important. And also ensure you watch the videos over and over again to ensure you get the full information I try to give out in this section. So in this section, we are trying to look at how to draw bending moment and shear force diagram for a simply supported beam. Now this is just an introduction to structural analysis. In engineering, civil engineering per se, what we call structural analysis. So we are trying to look at how to draw bending moment and shear force diagram. We have done how to draw bending moment and shear force diagram for cantilever beams. But for this, in this section now, we're going to be looking at how to draw shear force and bending moment for simply supported beam. Now, what is a simply supported beam? That's the first thing. Now, let me just draw one so I see it. A simply supported beam is just like a beam that has a pin support at one end and a roller support at the other end. That is what we call a simply supported beam. It's a beam that has a pin support at one end and a roller support at the other end. And a roller support at the other end. So everything still follows. If we are drawing bending moment diagram, I like drawing the negative moment to the positive y-axis and the positive moment to the negative y-axis. That's what I like doing. And for shear force, I follow the y-axis just as it is, positive to positive, negative to negative. But you can also do it the other way around. The thing is still good. So find the values of the movement are absolutely correct. So what we are going to do in this place now. First, let's look at the case of a load, just a point load, having a span. Let's say the point load is having a span, or the point load is having a span of, let's say, 4 meters, and the value of the load is 10 kilonewtons. Now, how are we going to draw the shear force and bending moment diagram for this load? How are we going to get the shear force and bending moment diagram for this load? It's just a question from the beam shown below. Now, you should know that it is a simply supported beam or it is a cantilever beam. I told you cantilever beams are beams that are fixed at one end and free at the other end. But this one now is both having supports at both ends. But one of them is a pin, the other one is a ruler. It will be a pin and a ruler, or what we call it a simply supported beam. Remember, we have overhanging beams, we have fixed-ended beams, we have continuous beams, and so on. So most of the beams are just called extension from that overhanging beam that can still be like a simply supported with overhangs. Overhang means this one will not be spanning or the other side will be spanning. Both will not be at both ends. That means it is not having overhangs. So we have what we call indeterminate problems. But this one is determinate. If you put pin and pin in this place, it will become indeterminate. That means we cannot solve it with the static equilibrium equation we have looked at in our first or one of our videos in this channel. Though you have not looked at that, we have looked at static equilibrium equation, force equilibrium, and supports we do use in structural mechanics. So this is just a simple example on how to calculate bending moment and shear force diagrams. So what do we do? The first is to draw the free body diagram. Let's go free body diagram. So let's draw out the free body diagram. Now, how many reactions does a ruler have? Just one. You see. Let us say point A, point B, point C. So that's our arrow A. You have just one reaction. Is the vertical reaction. For a ruler, we'll have just one. Then you can just that's the reaction. Then we'll draw the beam. Then how many reactions do we have in a pin support? We have vertical and horizontal. That is all. There's no movement. There's an arrow B for the horizontal, arrow B for the vertical. Now, because there's no horizontal loading, this arrow B will be latent. It will be hidden. It will not be active. It will be dormant. There's no action from it because if there's any action, let's not have reaction. There's no action for it. We only have vertical load that is giving us the action, which is 10 kilonewtons. The next thing, upward force will equal to downward force. Upward force is arrow A, and another upward force is arrow B. So arrow B that has just V, so that gives us equal to, and the upward force, the downward force we have here is just 10 kilonewtons. So the next thing, we cannot solve that. It's not possible to solve it. It's not possible to solve it. So what are we going to do? Because we have two unknowns in one equation, we cannot solve it. We cannot solve that problem. So the next thing, we're going to use another static equilibrium equation, which says that the sum of moment about any point should be equal to 0. The sum of moment about any point. When you sum up moment about any point, not moment about the point, but the sum of all the moments from maybe the left and right hand side about a particular point should be 0. So let's say the sum of moments about point A should be equal to 0. About point A should be equal to 0, and let's take all anti-clockwise. Okay, let's take all clockwise moments to be negative. You have a clockwise moment, we call it the negative moment. Then you have anti-clockwise should be positive. Then, so that's our sign convention we're using here now. You can use otherwise. When I'm saying any clockwise movement will be positive, anti-clockwise movement should be negative. And any clockwise movement should be negative, anti-clockwise movement should be positive. And you can also say your clockwise movement negative, anti-clockwise positive, or what have you. So that's what I'm using here. That's the same convention I'm using here now. The next thing, okay, there's no moment at this point will be 0. And let's check. We have 10. So take a moment about point K. Remember, this 10 is acting at the center. It's acting at the center. In case you don't know, the from here to here is 2 meters. From here is also 2 meters. So please take note of that. Take note of that to be straight. It will be shown in the question. From here is 2 meters. From here is also 2 meters. So that's what I have. So we're going to have minus 10. 10 is going down, so it should be negative, times 2. Then this one is going up. Arrow B is going up. So now plus arrow B times, what is going to get to here? 4. Minus 4. Is there any other force again? No. So because this one is latent, it's just acting at the point horizontal direction, so there's no movement from there. So it must be equal to 0. So the sum of all the moments about point A should be equal to 0. So we will now be having 4 arrow B to be equal to minus, this time is 20, that is minus 20. So that if you divide both sides by 4, our arrow B will be equal to minus, that's okay, will be equal to plus. That's plus 20, because if minus crossing this side, we change to plus. So we're going to have plus 20, that's plus 5 kilonewtons. That's what we're having for arrow B. Remember, this plus is equals to 10. So arrow B should be equal to 10. If plus plus is change to minus, 10 minus arrow B. 10 minus arrow B that have 10 minus 5 that equals 5 kilonewtons. So our arrow B is equal to 5, our arrow A is also equal to 5. Why? Because you check, the thing is symmetrical. We have 10, just share it, it will carry half, because the distance between here and here, and this distance is the same thing. So we just cannot divide it by 2, and so that is the for also carry half, That's why it's like that. So the next thing, we start calculating moments about each point. Now, if the beam is not, especially when the beams are not having overhang, all this pin and roller support, you cannot resist movement. Okay, let's try and see what we are going to have. Now the first thing is, let's calculate movement at K. Okay? Let's calculate shear forces. Now for shear forces. Now, what is the shear force? What is shear force at A? What is shear force at A? Look at the shear force we have. It's plus, it's positive. Right? It's positive. So we have shear force as to be plus RB. And the shear force we're having what is the value of ROA? ROA is whether it's 5 kilonewtons. That's shear force we are having. Then the shear force from A to C. Remember this A, this B, and this C. From A to C will be, we don't meet anything. We don't meet anything. So we see 5 kilonewtons. Then shear force at C. What is shear force at C? At C we met a load of 10 kilonewtons going down. That will be negative. You have plus 5 minus 10. That gives us minus 5 kilonewtons. Minus 5 kilonewtons. Then the shear force from C to B. From C to B, there's nothing there. So it still remains at minus 5 kilonewtons. And what is the shear force at point B now? At point B, there's a load going on, which is positive B. And what's ROB there? ROB is 5. So we have minus 5, then plus 5. That gives us 0 kilonewtons. It must end. You see ends there. Remember the first one, did before for cantilever beams. So that is the shear force at each point. And let's go for bending moment. Let's go for bending moment now. Let's go for bending moments and see what we're going to have. Let's go for bending moments and see what we're going to have. Now, what is the bending moment at point A? What is the bending moment at point A? You can start from any point. Start from any point for this. There's no problem. What is the bending moment at point A? Now, at this point, there's no distance between this force at point A. So the bending moment at that point will be 0. So there's no distance there. That's 0 kilonewton meters. Or you can put units, you can follow by units. Because 0 is 0. Then what is bending moment? Bending moment at point C. What is bending moment at point C? The bending moment at point C will be this load times this distance. That is bending moment at point C. Remember that load is positive. That is plus RO. That is plus ROA times 2. That is plus ROA times 2. That is plus 5 times 2. And that will be equal to plus 10. Plus 10 kilonewton meters. Then, what is the bending moment at point B? What will be the bending moment at point B? If you check very well, there's no distance between this point and this load. So the bending moment at that point should be 0. So let's just check it. Let's try to come from here and see if it is 0. Let's try to see. So that will be ROA. That will be ROA times 4. That is ROA is 5 plus 5 times 4. Then this one is not coming down. So this load that is coming down now will give anti-clockwise movement. I already select clockwise movement. Okay, let's check this. Okay, for this in this case now, when we are doing this one now, our clockwise movements are positive, while our anti-clockwise movements, are negative. Clockwise movements are negative because that force is coming down. That's what we have in there. So that will be minus 10. Times what is done between this piece and this piece? 2. That will be 0 kilonewtons meters. Because this one gives you plus 20 minus 20. That's 0. That's 0. So let's draw the diagrams out to see what we are going to have. So let's just draw the diagrams here. Let me draw the diagrams here so that we'll see what we are having. So let's draw the diagrams in this place. Because of time, let me just draw the diagrams here. Let's draw the diagrams here. So I just have this, and also have this. So let's the shear force, we have a straight line. What is shear force at this point? The shear force at point A was plus 5. Plus 5. Just mark plus 5 to this place. Plus 5. Then the shear force at point C. The shear force at point C was minus 5. But from A to C was still 5. From A to C was still 5. So you know what you are doing. From A to C was still 5. And from C to B was still 5. Before you now get to 0. So we just ran with straight lines, horizontal lines, vertical. One was still the same. Horizontal. So vertical. This plus, this minus. This is what we're having as our shear force for this load. So we're having is 5, 5, 5, 5. So that's what we're having here. Then for the bending moment diagram, see how this line For this point, element of 4.A, element was 0. Or at this point, C, at point C, element at point C, what is bending moment at point C? Plus 10, plus 10. Remember, for plus will go downward. Plus will go downward to mark 10. What is bending moment at point, remember that plus is 0. So the next thing, we just draw a diagonal. Remember, for point O, we join a diagonal, I still straight. So just join a diagonal, and then this one, this with a diagonal. So this will give us the bending moment diagram for this problem. So we're going to have for this problem. So this is, remember, this positive. So this is what we're having. So this is how the bending moment diagrams. The beam tends to bend downwards. If this beam is active, you can see what we're having there. This is what we're having for this problem. So for example 2, I'm going to be looking at the case of uniformly distributed load. That's what I'm going to be looking at. Case of, example 2. Example 2 is this problem we're having. We want to look at a case of simply supported beam that have a uniformly distributed load. That is what we're going to look at now. Simply for supported beam with a uniformly distributed load. So let's look at this and see what we're going to have. Now the problem, the first one we're going to look at that is show that the maximum moment, that is the maximum bending moment, and maximum, that is the maximum bending moment for the beam above is this. For this beam, simply supported beam carrying a load equal to W with the span of L. The maximum bending moment is equal to this. So we should show it and check whether it is true. So what do we do? First thing, write solution. Then I just write out the free body diagram. Just draw the free body diagram. Then we show that to see what we're having. We show that to see what we're having. So we have our arrow A. Then we also have our arrow B. The horizontal loading will not be active. See, there's no, the horizontal reaction will not be active. So let's just forget about that horizontal reaction for that. So there's a horizontal reaction here, but it won't be active because there's no horizontal loading. This one is W and the length is L. The first thing, upward forces will be equal to downward forces. The upward force of arrow A plus arrow B should be equal to W times L. Remember that for a uniform distributed load, one of the line of force, the more you multiply the span. I already explained that. So for this uniformly distributed load now, when we convert it to force, we use the load to multiply the length of the load. That will give us the equivalent value as a force. So that will give us W. That's what we're having. The next thing, let's take moment. Take moment about A. Let's take moment about this point A. And so we're going to have. So all clockwise moments will be negative and clockwise moment will be positive. Let's do that one. So once again, the sum of moments about A should be equal to 0. All clockwise moments should be negative. In this case, you can take clockwise moment as positive and the clockwise moment will be negative. I'm doing that way. So let's go. Moment about this point, we're going to have W, that is the first force I'm having from this point now. About A will be the moment comes from arrow A will be 0. Since we are taking at point A. So we're going to have W times, okay, remember W is coming down, so negative minus W times the length is L, that is the force, and after you are converted into force, I'm multiplying with the length, the force will be acting at the center of the loop. What is center? Means the half of the full distance. What is the half of W? What is the half of L? L over 2. So that is the time we are going to multiply it with now. The distance between the center and this point we are taking the moment for now will be L over 2. So the distance between the center and this point is L over 2. And the distance between the center and this point is L over 2. Plus arrow B times the full distance is L over 2. That is arrow B times L, that is full distance, will be equal to 0. So the next thing we have minus WL squared over 2 plus arrow BL should be equal to 0. The next thing, arrow B L should be equal to WL square over 2. So this will cancel this. Our RB will be equal to WL over 2. That's what we're having. Remember, RB plus ROA is WL. So ROA should be the same thing as WL minus ROB. That is WL minus WL over 2. So it's going to give you difference over 1, with LCM is 2. Now give us 1 into 2, that is 2 times that is 2 WL minus 2 to 2, that is WL. Give us WL over 2 as well. So you see, both of them are carrying the same load because it's just symmetrical. There's no thing that is, this one is carrying equal load with this. So the next thing we're going to do now is to look for the bending moment. Now, where is the bending moment maximum? Where is the bending moment maximum? Actually, the bending moment is maximum where the shear force is 0. That's where the bending moment is maximum. Where the shear force is 0. And where is the shear force is 0? We don't even know where the shear force is 0. How can we get where the shear force is 0? We come, okay, let's develop an equation so that we'll get our shear force to be 0. Just come, let's develop an equation now. We take a little distance to any point. Just take a little distance from any of the ends. Just take a little distance and call the distance x. Let's call it x. Let's call the distance x. Then let's take moment about this point x. That's what I'm going to do now. I'm going to take moment about that point x. Okay, let's say moment at x. Now, if it is anti-clockwise, it will be positive. It's going to be positive. If it is clockwise, it will be negative. If it is anti-clockwise, okay, let's do this way now. Let's say if it is clockwise, it will be positive. And if it's anti-clockwise, it should be what? If it's anti-clockwise, it will be negative. Let's talk about that now. You know what the first one will be? If it's clockwise, it will be negative. If it's anti-clockwise, it will be positive. Now we have changed the sign now. So you can do it you can just pick any sign that is convenient for you. So look at what we are going to have there. We are going to take moment about this point now. We're going to take moment about this point. So moment about point x. Okay, let's not tell the sum of moments about point x. Or you can also do that. You can also say moment at x will be equal to moment about this point to moment at point x will be equal to ROA times x. That will be ROA times x. Then remember this load is coming down. That load is coming down. Remember coming down will be minus W times what is the distance between this point and the point you are taking for x. That is x. That is the force. Then the force will not be acting at the center of this x. What is the center of x? That is x over 2. 2 times x over 2. That's what we're going to have. That's what we're going to have. So the next thing, we're going to have something like this. ROAX minus WL squared over 2. That's what we're going to have. So this is the movement equation for this simplest of order be about any point x. About any point x. I can ask you what is the movement at s is equals to 0. That is at this point A. And the moment will be 0. I can ask you what is the movement as s equals to L over 2. You give me the movement. But we are looking for that. What we are looking for is where is the movement maximum? Now, there's something you are going to do for me now. You have to know that the moment is maximum where the shear force is 0. That's why we have the maximum moment. Now, how do you get shear force from this moment equation? Now, if you differentiate shear force, if you differentiate bench moment, you're going to have what we call shear force. That's what we're going to have. We're going to have shear force. So if I'm going to differentiate this moment now, I'm going to have what we call shear force. So let's differentiate and see. So d of our mx over dx will be equal to differentiate this one. I'm going to have ROA. Differentiate this one. I'm going to have this times this. That will be 2wx over 2. That will be ROA times w. Okay. Minus this one can do this wx. That's what I'm going to have. So this is called shear force. This one is called shear force. So we can call this one, also call this one shear force because we have differentiated the movement. That's the shear force. Now, the bending moment is 0 when this the bending moment is maximum when this shear force is 0. So when this shear force is 0, we have our maximum bending moment. So what is the value of x if this shear force is 0? What will be the value of x? So actually, our s will be, let's get moving on to this other side, we have wx is equal to r. So we have wx is equal to ROA. So s will be equal to ROA over W. Now what is ROA? What is ROA? Our ROA is equal to WL over 2. We have WL over 2 then divided by W. Divided by W. And if you turn this one to times, we take the reciprocal of this. So this one will cancel this. So our s will be equal to L over 2. So actually, it is when x is L over 2. That's when we're going to have, that's the point we're going to have maximum bending moment. That's when x is L over 2. So now we're okay. Now maximum bending moment will come when x is what? L over 2. That's when we're going to have our M maximum. So what is the moment at that point now? We will have our ROA. What is our ROA? Our ROA is WL over 2. WL over 2 times our S should be L over 2 for maximum bending moment equal to minus W, our L over 2 square over 2. So I'm going to be having something like WL square over 4 minus W all square over 4 over 2. So I'm going to be having WL square over 4 minus WL square over 8. And WL square over 8. So last case, okay, let's solve the last question here. Let's solve the last case here. The last case will now be our maximum bending will be equal to, we're having WL square over 4 minus WL square over 8. So just go to rule a line. What is the sum of 8 and 4? We have 8. We have 8 of already. So 8 divided by 4, that's 2. 2 times this, that's 2WL square. That's 2WL square. Minus 82, that is WL square. To give us, so our maximum moment, our M maximum will now be 2 of this minus 1 of it. So give us WL square over 8. So that's what we will have. Remember this, we show that the maximum moment is WL square over 8. So this is what we're going to have as our maximum bending moment for a simply supported beam and is carrying a uniformly distributed load W and a span of L. So that's what we're going to have as our maximum bending moment. So we're going to learn how to draw more shear forces and bending moment diagram for a simply supported beam. So that's the next thing we'll be looking at in our next section. So this will be the end of this section. In the next section, we're going to look at how to draw bending moment and shear forces diagram for a simply supported beam. So see you guys in our next class.